Hey, year 13s, thanks for coming, guys. I'll throw the link for the YouTube video up onto our chat. It'll take a second for it to start anyway. I'm going to throw it onto my 13 Meet. There we go. It's up. So this is actually this is Carbons and Chirality Part 2. Just waiting for it to start. There we go. There we go. Done. Tenzi's in. So that's up and running. I can't have the chat, unfortunately, running today, guys, because I've got Winkett and Julian in the class. So I'm just going to crack straight on. It's nice to see that you're there, Tenzi. There we go. Share my screen. We're up and running. Hey, Dixon, good to see you. So here's my lesson for today. So last lesson, if I just do a quick summary of last lesson, we were doing chirality part 1. And what we were doing is we were looking at our learning objectives was to understand the mechanism with shapes. So this was nucleophilic addition of carbonyls, and we talked about this idea that they are trigonal planar and that nucleophiles can attack from above or below 50% of the time. What that means is we end up with two products being made in a 50-50 mix. We call that mixture a racemic mixture or a racemate, but it also means the resulting carbon ends up having 4 different groups, which is called a chiral carbon or an asymmetrical carbon atom. And we started drawing them. We looked at the fact that we have 4 different groups. And those 4 different groups give this very unusual property of it being optically active. So by the way, that's the one thing I didn't mention in this lesson. Another word for chiral carbon is an asymmetrical carbon atom, so just bear that in mind. We then talked about separation problems because a chemist can't separate them. The chemist cannot tell them apart. Same reactivity, same boiling point, same everything, but they are separated through enzymes. Biologists can separate them because they have different drug properties because of the lock and key fit with enzymes. So today's lesson, we're moving on to optical activity. So how do we find out about this idea of there being a chiral carbon? So 3 learning objectives. Number 1, know the test for optical activity. Number 2, be able to name enantiomers. DRS and DNL, I'll explain that in a minute. And then the last one is to understand Sn1 and Sn2 from an optical perspective. So first thing I need to do is we need to talk about the pointless test. Yep, testing for optical activity. Testing for optical activity. So let's draw a molecule. Let's go carbon. I want it to be asymmetrical. Asymmetrical. Is it spelled with a double M? Yes. Asymmetrical carbon atom, which means I need 4 different groups. So I'm going to go A, got to draw it 3-dimensional, B, and D. Right, we now know, thanks to last lesson, that this carbon is chiral or asymmetrical. It is going to be optically active. So what I'm now going to do is I'm going to test it for this. So this is where what does the word optical mean? So here's the steps. So here's the test. Step 1. Take a pure sample of 1 enantiomer. Right, I'm going to explain that a little bit more. So we now know that there's 2 versions of this drug. We've got A, we've got B, we've got C, and we've got D. But we now know that there's another one, a mirror image. And we need to be able to draw it. A goes up again, the wedge goes forward again, but now the B and the D need to be switched as a mirror image. Now these are called enantiomers, and they are given letters. You guys remember geometrical, don't you? Geometrical is when there are different groups on opposite sides. So A and A, and then B and B. We would call this one an E isomer, yeah, an E-geo, versus the other one where they're on the same side, which is the Z isomer. They pick up the same, a similar lettering for optical, and they called it, so this one is called the D isomer, which stands for dextro. And dextro in German, I think, means right. The other one is the letter L. I ought to color code this. D and L. And the L stands for levo, which, surprise, surprise, means left. Now, there's actually two other letters which sometimes people use. You can also have R, which is rectro, R, which is rectro, which means right, and S, which is sinister. Sinister. And that's because the people who are left-handed are sinister. They're evil. Anyone here left-handed? Excellent. That's the right answer. Don't like left-handed people. They're evil. They're sinister. So now here's the really stupid bit. People often go, so how do you know which one's the left one and which one's the right one? You don't know until you test it. So you cannot just look at a picture and define if it's left or right. Really stupid. I think there is actually a method for doing it, like using like a piece of paper or something. I can't remember what it is. But you need to test them. So take a pure sample of one enantiomer. Let's now go in brackets. Let's stick with R and S. Let's take R. So this is the right one. Yeah, we're going to take pure R.
So we separate first, right?
Sure. It's called the pointless test for a reason, Winkit. Step one, take a pure sample of one enantiomer. Right, let's draw this as a picture. Here's my pure sample in a little cuvette. A little cuvette. Here's my pure R. Pure R. Right, what I'm now going to do is I am going to shine through that pure R. I'm going to shine through it. Plain polarized light. So step number 2. Step 2, shine plain, change my color, notice. Plain polarized light through sample. Second?
Does it matter like if it's a parallel to ground?
What a great question, Winkit. I've never had anyone ask. The answer is, it doesn't matter. Doesn't make any difference. Right. So Winkit's asking a really good question, by the way, guys. This is actually really hard for me now to draw, because if you were to look, if you had a torch, and you were shining your torch, you know, you get your beams of light coming out at you in yellow, your beams of light coming out. What you'd realize, what we don't even realize is happening, is that the light is actually, you can actually treat light as a wave. And what you can say is that the light is actually leaving in all planes. You're impressed, but I was actually really close to being really good there. Oh, okay. I know, but I'm doing it for the other people on the channel as well. Julian is so selfish, God. So what that means, so it's actually leaving in all planes. So some are vertical, some of these are going up, down in the vertical plane. Some of them are going horizontally, yeah, which are these ones. That's the horizontal one, yeah. So so here's the vertical. Yeah, the vertical going up and down, and then the horizontal. Yeah, my drawings are amazing. You've also got ones in this direction. Yes, these are like that, you know, slightly twisted. Yeah, some are vertical, some are horizontal. So they're actually leaving in all planes. Now, what we discovered was that you can actually filter these. You can filter them out. This is how they make 3D cinemas, by the way, if you're interested. Polarizers, correct. So we can actually take this 3D, this all plane light, and we can put it through a filter. It's called a polarizer filter, brackets, polarizer. Yeah, and what will happen is, what comes out is one plane, just one. So this one comes out as the whole, it blocks everything out.
It's like long chains of molecules, right? Like long chains of long slits. The slits, right? Yeah, like long, yeah, it's like suddenly
it's actually way more complicated than that, I think.
It's like parallel to the slits.
I think it's actually incredibly complicated from it's actually all chemists doing all the work as well, designing molecules that absorb certain, it's complicated. You can find out a bit more about it actually, maybe let me know, because I might be wrong. But anyway, so we're gonna filter out the light so we get one plane. And we're actually gonna choose let's go for the vertical plane. I like the vertical plane. It's easy. Yeah, the vertical plane went through. Now, here's the really cool bit. Shine plain polarized light through the sample. And here's step 3, the observation. It will be rotated. It will be rotated to the, and which one will be to the right, or left, by equal and opposite angles. I'll explain. Opposite. This is where right and left came from. Angles.
So in this case, it will be to the right.
Correct. So if we did, torchlight, single plane, yeah, going in, and it was a vertical plane that we'd chosen. Yeah, this is what we shined at it. It goes through our cool little optically active sample, and out comes on the wall that it has been rotated from 0. And in this case, it's been rotated to the right. So this will now be an R. If it had been the left version, yeah, if it had been the left version, it would have been rotated by equal but opposite angles, yeah, to the left. So that, no, it's not by 90. By the way, equal and opposite angles, the angle actually varies. So some will move it only 2 or 3 degrees, and others will move it much larger amounts. I don't think that will happen, actually. I mean, that would be awkward as hell if it did that, right? Because it'd just be still the same straight line. Anyway, so now the question is, why do I keep calling this the pointless test? By the way, guys, you've got to learn that. Learn that. Equal but opposite. Just take a pure sample, shine plain polarized light. It will rotate the plane of light. Rotate the plane of light to the left or to the right by equal and opposite angles. You just have to spit that out when they ask you in the exam to describe the test for optical activity. So here's the really stupid bit. So why is this pointless? Because what would happen if you did this test and you shone it through a race meet? You see absolutely no change. Racemic mix, we see no change in rotation. And guess how we make optical activities? Optical molecules? In 50-50s. So the test will always be negative. It's so stupid. So I've got a question. So here's a bit of history behind this. So how the hell did they discover this in the first place? It was a French chemist who was a bit of a drunk. I can't remember what his name was. And he was a chemist. He worked in France. He had loads of wine glasses all over the place. And he drank a lot of red wine. He lived nearby a red wine vineyard. And one day he wakes in the morning to a hangover, he looks over the suspect with wine glasses and sees this. One of his red wine glasses that has been there for a couple of days. And it left a little bit of red wine at the bottom of it, and it evaporated. And of course, what was left were these beautiful red crystals. And the crystals had a really bizarre iridescence to them. So of course, he took some of the crystals out and on the microscope and had a look at them and realized that the crystals had a very, very specific arrangement. All the crystals were facing in the same direction. The next thing is that he considered there were very particular types of iridescence happening in the sample. And what he realized was that there must be something going on in the molecules that's changing what's happening in terms of the light. And the molecules also be quite similar. Now it turns out that because our bodies function on enzymes, we are a giant walking enzyme, I agree? What that means is our bodies tend to make L. We primarily, all living organisms tend, it's not always the case, but it's a high probability that if you pull out a molecule that's optically active from a living organism, it will probably be L. And we also respond better to L as well. So the left-handed side, which is hilarious because they call left-handed sinister, maybe similarly now, should we respond more to the right? It's possible that. But anyway, the point being is, we know that there tends to be a trend in which one we respond well to. So when we make dip R and S, we know that one of them's going to be good for us and one of them's going to be bad for us. Chances are the S is going to be probably bad than the other. But yeah, it's because of our enzyme lock and key fit thing that makes everything different. And so it was discovered through looking at the crystals in red wine, because the Greeks were making primarily L. Yeah, really, really cool stuff. They then, of course, took half a decade to figure out how to polarize light, and then they started. Someone came across this paper and went through and did the test, and they confirmed it. It's really interesting. So anyway, this thing does come up, but it's a bit of a pointless test because everything's made racemic. And I'll show you some exam questions on this in a minute because it's a bit stupid. But test for optical activity, R and S and DNL were done. Right, Sn1 and Sn2. We're nearly at the end of the lesson, actually, which is quite nice. Nice quick lesson today. I will look at some exam questions. So, can you put a little title of my laptop needs restarting. Sn1 versus what's happened?
No, I tried to take a look and see if there's any questions from attendee and the all. But apparently, this video is restricted. Please check the Google Workspace.
Oh yeah, you're not allowed to watch it in school. I don't know why.
What? I just watched it.
I know.
Oh, maybe student can?
Don't know. Anyway, what? Sn1 and Sn2 Optical. Right, guys, you ready? So, Sn1 and Sn2, this has nothing to do with carbonyls, does it? No, we know that Sn1 and Sn2 is nucleophilic substitution, one species of the rate determining step or two species in the rate determining step. Let's remind ourselves of this. So we're going to go, let's do nuke sub with this, nuke sub with this guy, CH3, 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 and I'm going to do Cl, yeah, and then I'm going to do this guy. Right, Winkit.
Yes.
So first of all, can you classify him, please?
Classify as in tertiary.
Thank you very much. Good job. That is a tertiary. Thank you, class. Yeah, class is a tertiary halo alkane. Well done. Julian? Thank you very much. A primary halo alkane. Next, Winkit. Sn1 or Sn2, please.
Sn1.
How do you know?
Well, I just remember that it just breaks off, and that's why this molecule is the molecule in the rate determining step.
Well, so you're absolutely correct. This is Sn1, not Sn2. And you're right. The reason being is which one is in the rate determining step then? Well done. The rate equals K brackets tertiary halo alkane. No OH minus. Agreed? Yeah, the concentration of the halo alkane is going to matter. And then we go to primary and we go, this is Sn2. The reason being is the OH minus in the attack now, because it doesn't break off because of this polarity. Yeah, both of these are now going to matter. 2 species in rate determining step. So rate equals K, and then we're going to have OH minus ions and the primary halo alkane concentration. 2 species in RDS. Yep. So, yes, that's correct. That's why. Winkit, yes, because it's like this. Yeah. Because it's just the positive inductive effect lowers the polarity, which means the OH minus just can't see it. Yeah, it's just like this. It's like, well, I don't see anybody. Yep. Right. So here's the really, really cool bit. I love this bit. It's one of my favorite bits. So, thought experiment. Ooh. So, if I went and got this, right? Okay, guys, would you agree that's tertiary?
Yeah.
But there's also something important. Julian, is this chiral or non-chiral? Well done. This is an asymmetrical carbon atom because group 1, group 2, not the same group, bigger, not the same group. This is optically active. So, the really, really cool bit of this game. We know that this is optically active. I'm going to pick, which one do you want, Winkit? Do you want R or S?
S.
Okay. So Winkit's going to go and select the S version. Winkit, can you now really impress me? Can you name that? Let's see how long it takes you to name it.
Name like just that.
Just give me the organic name of that.
1, 2, 3, 4, 5, 6. That's a
Well done.
1, 2, 3. So that's a 3 chloro. Yeah, 3 chloro, 3 methyl. Same.
Well done. Guys, really impressed. Can I just say, if I had that in an exam, I would, of course, always straighten it out. But well done. Really, really impressed. You spotted the longest chain. Yeah, there's the longest chain there. Realizing that you then count from this direction because there's a smaller number here than here. So that's going to be carbon number 3. So that's going to be a 3 chloro. And I'm really, really impressed, guys. Well done. That was a real challenge, that. And to do that in your heads, I think you probably did a better job than I did. Well done. So he's picked S. Now, here's the cool bit of this. Because you've picked one enantiomer, we're now going to put this to nuke sub with sodium hydroxide. So, Julian, if I do nuke sub on that sodium hydroxide, what am I going to make? I like it. Great job. Chances are we're going to switch this out and turn it into an alcohol. Now, it could have done something else from this. Could we make it out? Would this be wanting to make an alkene? Let's go through elimination. It definitely could. Definitely could. We tend to realize that we can select for this, though, because in reality, the nuke sub it's going to go through is going to be Sn1. And it depends on more of the halo group, really, more than the tertiary. Tertiaries tend to favor elimination rather than nuke sub. Tends to. Primaries, secondaries will do both. Primaries tend to go for nuke sub. Yeah? So, here's the cool bit though. It will do nuke sub, And this is actually what we'd be designing it to do it. Oh, Julian, what conditions? If you wanna select for nuke sub, what conditions are you gonna choose? Elimination and then the opposite. That's the way I do it. I only have one in my head. No. So I got elimination. For elimination, I'm going to go for concentrated hot ethanolic sodium hydroxide. What's the opposite of concentrated? Dilute. What's the opposite of hot? Hot is warm. You're not allowed to say cold. The reason being is all organic reactions are breaking and making covalent bonds. You're breaking covalent bonds, you need to keep so everything needs to be it's warm. Yeah? Although that's not true. When you're doing nitration of stuff and azo dyes, you have to do it cold to prevent further substitutions and things like that later. But anyway, so warm, what's the opposite? What's the opposite of alcohol? Yeah? So we've got aqueous. So we're gonna push this towards nuke sub. So the conditions we're gonna do sodium hydroxide in warm aqueous dilute. Yeah? And what's now gonna happen is, so nobody ever asks how we know about this Sn1 and Sn2. Everyone just kind of goes, okay, right, so it does that. Okay. What's the evidence for it? How do we know that this is going to be it? And one of the ways that we know is because of this. We can put in pure S. Now, if I do nuke sub, I should get pure S back out, right? No, don't see, why would you not? Like, I put in pure S, they would have expected pure S out. But you don't. You get a race mate. So in goes pure S and out comes 50-50 S and R. And the question is why? And the reason is the change in shape, thanks to Sn1. Because what's going to happen is it's going to break away. And we're going to get this product. I think you can see what's going to happen, can't you? It becomes trigonal planar.
Ooh, what's like that?
So it started tetrahedral, and then because it's Sn1, it forms trigonal planar. Trigonal planar. And what that means is the nucleophile can attack from above or below 50% of the time. How about the other side?
Does that make any sense? Like, let's say
No, wink it. Remember, the 5th of November. Remember, hang on. Remember, this is actually flat, wink it.
Oh, yeah.
Yeah, they're attacking, yeah, above and below. They're not attacking into the gap. Yeah, they're attacking above and below it. Yeah, but because Sn1 becomes trigonal planar as an intermediate, what that means is I spit out a 50-50 of R and S. Here's the next cool bit. What about Sn2? If I have a primary, something like this. Oh, hang on a minute. Oh, yeah, primary. Can do this. Let's put on a. Let's make it secondary.
Oh, now we're making it secondary?
Yeah, well, I'm going to make it second. It will still do. It'll actually do a mixture of Sn1 and Sn2 now. But no, it doesn't matter. It doesn't make any difference. The reason is I want it to go in. See, I need it to be optically active at the beginning.
Oh, yeah.
Yeah? Because you're going to love this. Winkit, R or S, please.
R.
Okay? Winkit chooses pure R. Julian, Name it, please. Butane?
Butane, yes.
Longest chain? 2, 3, 4? Yeah. Forgot what 4 was. Fair enough. So Winkit, we're now going to get, like, we're now going to get Sn2 attack. What would you expect to come out?
Would it be easier for them to attack from the top? Or would it still be a bit? It's not 56. Would it just be a 100 to 0? Or would it be the top, right? Would it be right as well? Or would it flex?
I know, right? It flips. It does. It does a funky umbrella trick of it inverting itself. Let me show you why. Because it's actually 3-dimensional. So I've got an R there. Oh, I shouldn't do that. I'll do CH3 here. And what we realize is when this, I'll put the H there and the C2H5 here. What we realize is the nucleophile attack in reality, yeah, here, what it's going to do is it's not going to come in from this direction over there, is it? It's not going to do that because it would be repelled by the slightly negative chlorine. It's going to attack from underneath it. And what it's going to do is these are going, so by the way, oh, I can actually show you this because there's actually an intermediate. So during that attack, this is the intermediate you're going to form. You form a trigonal bipyramidal transition structure. And what you realize is that it's folding itself inside out. Yeah, so these bonds here have all swung up this way, like an umbrella does when you fold it inside out. Now, by the way, this is now fully charged. The carbon has 5 bonds. This is bad. It's fully negative now, folks. You don't tend to put it on the carbon, you tend to put it outside. Because would you agree that you've gained a fully negative hydroxide ion conservation of electric charge? Yeah. Now you're going to have this break off, and the atoms continue to fold down. Yeah, and so you flip it inside out. Proper cool. Like, what?
Wait, the C2H5 also goes to the right? Oh, yeah,
it folds down. There you go. Flipped it inside out.
So from the left, it folds. Oh, I think I do the wrong thing. Oh,
so just to try and show this in molecule.
And then the CH3 will now just be normal.
So there is
You can always raise the net molecule.
There is.
I just used it just now.
Did you find one? I thought for real.
I don't use it just now. There you go. It was like this song.
hold on, 6. Oh, no, I found it! I found it! Right. So, I found it. So, the best way to show this is to show this as a long angle. It's actually a really horrible thing to try and actually show this. It's borderline impossible to compare this whole thing inside out. But what you need to remember is, and this is where I all this. This is where I probably ought to stop the video at this point, because I think I'm kind of done here with the YouTube video. Right, guys, I'm going to just play around with some Mollymod kids with Winkit and Julian. But I'm going to leave you guys be for the rest of the day. Have a nice rest of your day, folks. I'll see you all soon.